Welcome to the video tutorial on logistic regression. This presentation is in partnership with the Data for Impact project, also known as D4I. D4I works to generate strong evidence for program and policy decision-making, build individual and organizational capacity, and enhance the use of data for global health programs and policies. In this video tutorial, we will review the logistic regression analysis, things that need to be considered when using this method, and we'll have a stated demonstration. As part of the tutorial, we have several resources available: a background information sheet on logistic regression, the presentation used today, as well as a data do file, sample dataset used in the presentation. The do file and sample dataset are helpful if you want to perform the analysis alongside the presentation. So our objective today is to create video tutorials on how to use specific methods and commands to analyze routine data for evaluation and research. Keeping in mind that this video is not intended for beginners, but for those who have some experience with data analysis and Stata, the statistical software we will be using. We'll explore two analytical approaches used to evaluate routine data. The first is interrupted time series analysis, and the second, logistic regression. Our main focus in this video: more information on the different methods used to analyze routine data, as well as the materials used in this presentation, can be found on the D4I website. Now let's talk about logistic regression. Logistic regression, also referred to as a binary logistic regression, is a form of regression in which the dependent variable is a nonmetric or dichotomous or binary variable. Nonmetric variables are variables with values that serve merely as a label or means of identification. In addition to being non-metric, the dependent variable has to be binary or dichotomous, which basically means that the variable has two values. Example, yes or no, male or female, true or false. The analytical approach has extensive use in healthcare and social sciences, as well as other disciplines outside the field. For example, in healthcare settings, it's been used to develop multivariable clinical prediction models, such as developing a diagnostic prediction model that estimates the probability of a target disease being present or not present. And in the logic model, the log odds of the outcome is modeled as a linear combination of predictor models. Logistic regression has many benefits. First, the approach has gained widespread application in situations involving a binary outcome. Thus, many are able to interpret and understand the findings. It's easy to use and interpret compared to other more complex statistical methods. It produces robust estimates. It does not have the assumption regarding the distribution of classes, and the method can be extended to include multiple classes. And in doing so, you are conducting the multinomial regression. So like many methods, there are limitations. Logistic regression assumes that the exploratory variables or covariates are linearly related to the log odds of the outcome, while a linear regression assumes that the outcome and exploratory variables are related linearly. Logistic regression models are vulnerable to overconfidence, where it can appear that the model has more predictive ability than it actually has due to a sampling bias. In doing so, it overstates the accuracy of the predictions. Overfitting also occurs if the number of observations is less than the number of features. Collinearity between the covariates should be negligible or moderate, and if variables are highly correlated with one another, then the effect on the regression model becomes less precise. Lastly, logistic regression cannot be used for continuous outcomes. It can only be used to predict categorical outcomes. And so for this particular type of logistic regression that we're looking at, so the binary logistic regression, we can only use it for binary outcomes. There are also some assumptions that you want to confirm are not violated before conducting logistic regression. So the first is that the dependent variable should consist of two categorical independent or unrelated groups. An example will be gender, so whether you're male or female, or treatment type, whether it's medicated or not medicated, or educational levels, so whether you're primary or secondary or undergraduate or postgraduate, and so on and so forth. So your variable, your dependent variable, needs to be dichotomous. In addition, the two categories of the dependent variable need to be mutually exhaustive and exclusive. The second assumption is that the model should have two or more independent variables that are measured at the continuous or nominal level. So examples of continuous variables include height or temperature, and examples of nominal variables include gender, so male or female, or a profession. So you can have four groups, so whether it's a surgeon, doctor, dentist, therapist, and so on and so forth. The third assumption is the independence of observations, and that there is no relationship between the observations. If the independence of observations assumption is not met, another type of statistical test will be needed. Assumption number 4 is that the data must not be collinear. If you remember a couple of slides back, we talked about this being a limitation of logistic regression. Collinearity occurs when you have two or more independent variables that are highly correlated with each other. Assumption 5 states that there needs to be a linear relationship between any continuous independent variable and the logic transformation of the dependent variable. And in 6, there shouldn't be any significant outliers, leverage points, or influential points. And if they are present, it indicates that the observations in your data set are in some way unusual and can have a negative effect on the model used to predict the value of the dependent variable. So in addition to the assumptions, it's important to make sure that the sample size used for the logistic regression is adequate to avoid overfitting the model and producing biased estimates. The calculation can be complex and nuanced depending on the prevalence or frequency of the event or outcome you're looking at. Based on research, Peduzzi and colleagues in 1996, as well as Long in 1997, suggested general guidelines. So keep in mind that these guidelines don't apply in all circumstances. So for instance, in rare events, you want to consider other things as well. So Peduzzi and his colleagues came up with a 10:1 recommendation, where sample size should be 10 times the number of covariates or predictors, which is K in our equation, and should take into account the proportion of successes or the event occurring, which is P in our equation. They also suggested that the minimum sample size should be 100. So if you were to perform your calculation and your N is below 100, you still want to have at least 100 subjects in your sample. So Long in 1997 suggested that anything less than 100 cases is considered risky, and a minimum of 500 cases are adequate for the sample size for the logistic regression, and that there should be at least 10 cases per predictor. So as a reminder, in our logistic regression, we're predicting the probability of our event succeeding or happening. So our outcome will have two values, 0 and 1. 0 represents failure or the event not happening, and 1 is to represent success or the event happening. And then in our regression, we can produce either the odds or the odds ratio. So when we produce the odds, also known as the log odds, we're transforming the probabilities through a log link function and creating a new variable called logit. This new variable is on the left side of our equation. And so if you look at the equation, it may look familiar, mainly because it's kind of similar to the linear regression, with the exception of the left side of the equation. The left side is different because we're using a different approach to estimate the regression coefficient. So we're using the log link function and creating the logit. In the regression coefficients, or the odds derived from the model, which is our beta, it tells us the change in the expected log odds relative to 1 unit change in X, which is our predictor, holding all other predictors constant. Or you can interpret it as the predicted change in logits per unit change in a given predictor, controlling for other predictors or covariates in the model. So notice that we are talking about the change in the expected log odds or predicted change in the logits. Thus, the regression coefficients or odds or regression slopes should not be directly interpreted as the amount of change, but rather should be interpreted for the direction of change. When the regression coefficient or odds is greater than 0, then it's a positive association. And this implies that with each unit increase in the covariate variable, the log odds of being a success increases. When the regression coefficient of odds is less than 0, then we have a negative association, whereby each unit increase in the covariate variable, the log odds of being a success decreases. And finally, when the regression coefficient of odds equals to 0, then there is no association, implying that there's no increase or decrease in the log odds of being a success. So the logistic regression also generates the odds ratio. And so this is a more widespread method of presenting the results. And so to produce the odds ratio, we're finding the anti-log of the regression coefficient, or the odds that we talked about previously. So for this, we can interpret the amount of change. So the beta produced in our regression is the odds ratio, and it can be interpreted as the change in the odds of success relative to the 1 unit change in X, which is our predictor, holding all other predictors constant. The odds ratio is a ratio of the probability that an event occurs to the probability that an event does not occur. It's a ratio, so it takes the value between 0 and positive infinity. It cannot be negative. Odds ratios greater than 1 represent a positive logistic association. So the odds associated with the event success increases with each unit increase in the predictor. Odds ratio less than 1 represents a negative logistic association, whereby the odds of a target group membership decreases with increases in the predictor. And odds ratios equals to 1 represents a lack of association or no association. So there's no change in the odds per unit increase on the predictor. So the positive logistic association, which is when the OR is greater than 1, corresponds with a positive logit association when the odds is greater than 0. Similarly, a negative logistic association when the OR is less than 1 corresponds to a negative logit association when the odds is less than 0. And when the OR equals to 1, that corresponds to when the odds is equal to 0, and they both indicate no association. So the 95% confidence interval is also useful for the odds ratio and tells us whether or not the association is statistically significant. So if your 95% confidence interval includes 1, then your association is not statistically significant. So that means your p-value is greater than 0.05. And if your 95% confidence interval does not include 1, then your association is statistically significant. So that means your p-value is less than 0.05. Let's take a look now at the stata code or syntax. So the command used to obtain the odds is the logit. So you first identify your command logit, then you indicate your dependent variable, which is a binary variable. So it's going to have 2 values, 0 and 1. And then you list your dependent variables that you're including in the model. For odds ratio, there are 2 ways in which you can ask Stata to run the odds ratio. So the first is built upon the syntax we use for the odds. So you have your logit, then you indicate your dependent variable, and then you list your independent variables in the model. Then at the end, you add comma OR. And so this tells Stata to produce odds ratios. Alternatively, you can use the logistic command in place of logit. So then you have your dependent variable, and then you list your independent variables. So in the syntax, there is a need to distinguish between the different types of independent variables. For continuous independent variables, the variable can be entered as is or adding the prefix C dot before the variable name. For instance, age. Assuming age is a continuous variable, we can either enter age as is, so as age, or add the prefix and it will be C dot age. With regards to categorical independent variables, it's a little bit more nuanced. So for variables with more than 2 levels, we need to add the prefix I dot before the variable name to let Stata know that it is a factor variable. In doing so, we're comparing the different levels in that variable to the reference level, the reference group. And the reference group is our lowest level. Taking education as an example, so if education was a variable in our regression, we will let Stata know that it's a factor variable by adding the prefix I dot. So the Stata will compare each level to the reference level, which is the lowest level. Assuming we have these levels in our education variable, no education has a value of 1, and it's the reference level, and every other level will be compared to no education. So primary education will be compared to no education, secondary education will be compared to no education, and higher education will be compared to no education. In some instances, you may want a different level in the variable to be treated as the reference group. This can be done by using the letter B, then indicating the level of interest that you want to be the reference group or the reference level, period, and then the variable of interest. So using education again as our example, and assuming we're interested in making our reference group or level primary education. The primary education is the second level in the education variable. We will have the code B2.education. So now in our regression, primary education will be the reference level. So every level will be compared to primary education. No education will be compared to primary education. Secondary education will be compared to primary education. And higher education will be compared to primary education. So for binary independent variables, we can treat it either as a factor variable, whereby we add a prefix I dot before the variable name, or we can enter it as is without the I dot prefix. So in doing so, we can treat it similar to the continuous variable where we can pick whichever one we want and we have an option. So there are various ways of selecting covariates for the model, and ideally it should be done a priori before the analysis begins and be based in theory or previous research. Once you have conducted your analysis and have the results, you want to report the following: a summary of the analysis performed, for example, stating that you run a binomial logistic regression and any other analysis that you used. Next, you want to provide information about your sample, including any missing values. You want to provide information on the examination of all the assumptions of the logistic regression, including remedies that you used if there were any violations. You want to report the use of methods assessing model fit, such as the Hosmer-Lemon score, also if you assess for multicollinearity. And lastly, you want to report regression coefficients and or odds ratios for the logistic regression model and the 95% confidence interval. Several studies have used logistic regression in the analysis when conducting research or evaluation and used routine data as one of their data sources. So in 2017, Rosenberg and colleagues used the 2017 antenatal HIV centennial survey and medical records of women to answer the question, what characteristics are associated with being recently infected or recently infected pregnant woman. And so from their survey, they collected information on the respondents' marital status, education, and partner's age. From the medical records, they got information on the age of the woman, her HIV status at enrollment in the survey, and the timing of ART initiation. Their outcome was whether or not a woman has been recently infected with HIV. About 9 years ago in 2012, Kaigamba and colleagues used data from hospital registries to determine which clinic and patient factors are associated with enrollment, eligibility, and start of ART. They had 3 outcome variables: patient enrollment in care and treatment, which was a binary variable with yes or no levels, advanced clinical disease stage that they defined using or as the WHO stage 3 or 4, again a binary variable, and low CD4 count, so whether or not the woman had a low CD4 count. And then in 2018, Agorinia and colleagues conducted analysis to answer the research question, what are the social, economic, and demographic factors that determine low birth weight? They used data from the Navrongo Health and Demographic Surveillance System. Their outcome was low birth weight or normal birth weight. So they defined low and normal birth weight using the WHO recommendations. So low birth weight was defined as a birth weight less than 2.5 kilograms and normal was greater than 2.5 kilograms. And so for more examples of studies using logistic regression and routine data, refer to our background information sheet that is available on the Data for Impact website. So we'll now demonstrate how to use logistic regression using a fictional data set. So we have two data sources to answer the research question: what factors are associated with a woman's satisfaction with the maternity care services? So our data comes from registries of a health facility and exit interviews conducted with the women before they were discharged. The routine data was collected from the health facility's antenatal and delivery records. And so from these registries, information was collected on the woman's age, her gravity, parity, type of delivery, so whether or not it was a vaginal or C-section, her gestational age of the pregnancy, and whether or not she had a syphilis or HIV test. The data from the exit interview included socio-demographic characteristics such as marital status, educational level, occupational status, and also the rating of satisfaction used to create the binary outcome. So to rate satisfaction, women were asked to rank on a 4-point Likert scale the level of satisfaction with the staff's friendliness, helpfulness, and the speed of service. They also asked whether or not they would recommend the service to a family member or friend. These ratings were summed to create an index such that a higher value indicated more satisfaction, and then a binary variable was created using the median split approach. After the median split, we created our outcome variable that we're going to use going forward. And it's a binary variable measuring the levels of satisfaction, so low versus high satisfaction. And so women with low satisfaction were coded as 0, and their scores were lower than the median. And then women with high satisfaction were coded as 1, and they had scores at or above the median. And so this is a snapshot of some of the variables in our sample data set. In the last column, we have our outcome variable, and you'll notice that we have 0s and 1s, which represent the two levels of satisfaction. So 0 being low satisfaction and 1 being high satisfaction. So now let's move on to Stata to demonstrate how to perform the logistic regression analysis. In this video, I will illustrate how we perform logistic regression analysis, as well as univariate and bivariate analysis. The data set has already been opened in Stata, so we're going to just go ahead and start the process. First, we would want to take some time to look at the different variables or types of data we have in our data set, and we can do this first with the describe command. So the describe command basically gives us information on the data we have in memory. And from this, we can tell we have 525 observations and 19 variables. It also gives us information on the storage type, the value label, and the variable label for each variable. And so in our data set, we have an ID variable, which is the unique identifier for each woman, the age variable, which tells us the age of the woman, a variable telling us about the working status of the woman, a variable about the marital status. Just age is the gestational age at delivery measured in weeks. Gravida is the number of pregnancies that the woman has had. Parity is the number of deliveries she has had, so the deliveries have to be over 24 weeks. And then the number of ANC visits she's had during this particular pregnancy, her ethnicity. We have information about the HIV testing and results. We have information again about syphilis, similar to HIV, so whether they got the test and received the results. Information about the type of delivery she had, so a cesarean versus vaginal delivery. And then we have the individual items used to create the satisfaction index. That was eventually used to create the binary variable that we'll be using as our outcome. So we have the variable about recommending facility to a friend or family member, the staff satisfaction, the satisfaction with the friendliness of the staff, satisfaction with the helpfulness of the staff, satisfaction with speed of service. And then we have our continuous variable, the index that was created by summing all the individual items in the index. And then the last, we have the binary variable, that's an outcome variable. And then we have a variable measuring the level of education of each woman. So we can also use the summarize command if we want to see how many observations there are for each variable. So summarize and So with this command, we get information about the number of observations, the mean, the standard deviations, the minimum, and the maximum. And so if you were to take a look at our age, we know that the minimum age of women in our data set is 15 years, the maximum age is 49, and the average age of a woman is 31 years old. And we can also get a quick glimpse about the missingness in our data. So we know initially when we looked at using the describe command, it told us that there were 525 observations in our data set. And we see that for each variable that we have in our output, there are also 525 observations. So this is some indication that we don't have missing data. It's not an issue. But to really explore missing data in your data set, you want to use the mdesc command, which is what we have here. And we're not specifying a variable after the command because we wanted to analyze all the variables in our data set. So running this, focusing on the missing column, which is the first or technically the second column, everything is 0. So it confirms what we found or what we suggested previously, that we have no missing data issues. So now that we've reviewed our data for missingness and know what the data consists of, we can now move on. We're also going to assume going forward that no assumptions for the logistic regression have been violated. So our data meets all assumptions that are needed for the logistic regression, as well as the sample size requirement. And in saying this, we're saying that we have adequate sample size for analysis. So before conducting the logistic regression, it's important to present the information on predictor variables or covariates that you're using in the data set and their relationship to the outcome variable. We do this by performing the univariate and bivariate analysis. This is also important to understand because it's going to determine the type of statistical test you can use or whether or not you can perform the logistic regression. And the univariate and bivariate analysis are important to present when publishing study findings in an academic journal or even a presentation or at a conference. So we'll go through these processes before conducting the logistic regression analysis. Let's go back to our do file. The univariate analysis is the simplest form of statistical analysis and explores each variable in the dataset separately. For categorical variables, you want to review percentages, and for continuous variables, review the means and standard errors as well as the standard deviations when the continuous variable is normally distributed, or the median or interquartile range if it's not normally distributed. It's also important to explore each variable mainly because of sample size issues. And if the sample size is too small for one category, it may affect your estimates for your regression and may also influence the kind of statistical test you can use. First, we're going to explore the outcome variable, which is categorical, specifically binary, using the tabulate command in Stata. So we're going to tab, and then our outcome, and we're going to run this. And so from our output, we can see that in our data set, about 45% of the women have low satisfaction and about 55% have high satisfaction. And so we can take this exact same command, tab satisfied underscore by, and add comma no label if we want to see the numbers associated with each level in our variable. So running this, we notice that we have 0 and 1. And 0 corresponds to low satisfaction and 1 corresponds to high satisfaction. And this goes back to our PowerPoint presentation where we said 0 is a failure and 1 is a success. And so for our logistic regression, we're predicting the probability of our success. So the probability of a woman having high satisfaction. You can also see this exact same information using one-way frequency tables. And so it's different because it shows us the label as well as the values assigned to the labels in one table. So you don't have to run it separately. So running this, you can see. So we know that 0 is low satisfaction and 1 is high satisfaction. It gives us the exact same information. You can also find the confidence intervals for the outcome or the variable that we're exploring using CI, proportion, satisfied, and the score by. And so it gives us a confidence interval for our proportion for those who have high satisfaction. So next, we're not going to do this in the demonstration, but it's important to also present the percentages of the individual items in the satisfaction index. And so this information isn't going to be included in the regression analysis, but it can provide an insight. It's also important for publication. And so by adding the number 1 after the tabulation, we're asking Stata to produce tabulations for each item in the command. Whereas if we were to say tab or tabulation, the command will only run for one variable. It will run a tabulation for one variable. And so we're telling Stata to tabulate the distribution of the 4 different variables used to create the satisfaction index. So actually, let's just go ahead and do this so we can get an idea of the things that makes up our binary outcome. So from this, we can say that about 31 or 32% of the women in the dataset will highly recommend the facility to a family member or friend. About 31% were very satisfied with the friendliness of the staff. About 26% were very satisfied with the helpfulness of the staff, and 28% or 29 specifically were very satisfied with the speed of service. And so we can do the same thing for our independent variables, which are categorical. And so we're looking at the percentage distribution of the percentages. And so tab 1, because we want Stata to run multiple tabulations at the same time. Once we tabulate our categorical independent variables, we can say that 55% of our population have secondary or higher education, and 45% have no primary education. 47% are married, 52% are working, 18% identified as clay ethnicity, 19% as storm, again 19% as strong, 21% as twilight ethnicity, and 24% as twinkle ethnicity. 33% had tested and received their HIV results, and 34% had tested for syphilis and received their results. 51% had a vaginal delivery, while 49% had a cesarean delivery. For our continuous independent variables, we want to find the mean and standard deviation. So using the summarize command, we'll list all the continuous variables we want to explore. And so this particular command should look familiar because it's the sum command that we used earlier in this demonstration to see all the variables in our data set and the number of observations associated with them. So running this, we know that we talked about this previously, the average age of women in the data set is 31 years. The average gestational age is 38 weeks. The average gravida is 3.7, or you can round it up to 4. And gravida, as a reminder, is a number of times a woman has been pregnant. The average parity, which is the number of times she's given birth to a fetus with a gestational age of 26 or more, is 2. And then the average number of antenatal care visits is 3. So we can go a step further in the summarize command and ask Stata to produce additional information, such as the percentile distribution, the variance, kurtosis, skewness, by adding comma det at the end of our summarize command. We're not going to run this, but just want you to know that the sum command has this capability. So next, we're going to continue to our bivariate analysis since we're done with the univariate analysis. So the bivariate analysis is an analytical approach used to examine the relationship between 2 variables. And so we want to explore the relationship between each covariate or predictor or independent variable in our data set with the outcome. which is the level of satisfaction. And as part of the analysis, we want to determine the level of significance using statistical tests. And these type of tests that can be performed depend on the type of variables. We know our outcome is binary, which is a categorical variable with two levels. Our independent variables are either categorical or continuous. Thus, we will use the Pearson's chi-square test to determine the significance between two categorical variables if we have adequate sample size. And if one of our cells have an expected frequency of 5 or less, then we'll need to use the Fisher's exact test. So when we don't have adequate sample size, we'll need to use the Fisher's exact test. We'll use the one-way ANOVA or the two-sample t-test for the significance between the continuous variable and a categorical variable, assuming the continuous variables are normally distributed. And it's important to note that the t-test can only be used when the categorical variables have two levels. If the categorical variables have more than two levels, so 3 or more, then you'll have to use the one-way ANOVA. The t-test is no longer an option. But since our outcome variable is binary, we can use either of these tests. Starting with a Pearson's chi-square, you want to use a tabulate command, and then you list your variable of interest and then the outcome variable. So in this case, M status, going with the first line, M status, and then our outcome satisfied underscore by. The first variable in your command, when it appears in a cross tabulation, is going to be the column, and the second would be the row in the cross tabulation. And so when you switch this order, it's going to affect your interpretation of findings. So keep that in mind going forward. And we're also telling Stata that we want column percentages by using the call after the comma, and then we want the chi-square value, which is our Pearson's chi-square. So let's run this and look at the results in the window. So our output gives us a key of the values in our tabulation. And so within each row, we have a frequency and a column percentage. And so let's look at the first row. So within the row that provides information about unmarried, our frequency, so 126 women are married and have low satisfaction. And then our percentage is the second row within that column. And we also know our p-values because the p-value is down here. Something else to note is there are row percentages and column percentages. So how do we distinguish between the two? So we know we have a row percent if your total in the row adds up to 100. And you know you have a column percent if your total in the column adds up to 100. So in this case, our column adds up to 100, and so we have a column percent. And so this is just a way to cross-check or make sure that what you're asking Stata to produce is what you're getting. And so our results indicate that the differences in marital status across the level of satisfaction were not significant because our p-value is greater than 0.05. So our p-value is 0.784. And going a step further, we can interpret results. So we can say that among women with low satisfaction, 54% were not married and 46% were married. And among women with high satisfaction, 52% were unmarried or not married, and 48% were married. And so we can repeat this process for the remaining categorical variables, but for the sake of time, we're just going to go ahead and move on to the analysis of continuous variables. For the bivariate analysis of continuous variables, we're going to perform the one-way ANOVA command. And in this instance, the order you present your variables matter. First, you want to list the continuous variable. So in this case, we're listing age. And then you want to list your categorical variable. And if you want the table of summary statistics, you want to include the tab command. And this table includes the mean, standard deviation, and frequency. So let's run this. Did this work? Yes, it worked. This is our output, as we can see. And so the analysis of variance indicates that the difference in the average age by level of education is significant because our p-value, which is 0.0087, is less than 0.05. And so women with low satisfaction was significantly older than those with high satisfaction. And so women with low satisfaction, their average age was 32 years, and women with high satisfaction, their average age was 29 years. So we can repeat this process again for each predictor variable, but for the sake of time, we're going to move on. And so another thing to note is that when your analysis produces a significant result, it can be an insight to your logistic regression. And this could indicate that the significant variables could potentially be significant in the regression. So it's important to retain them in the analysis. And as we mentioned previously, you can also use the two-sample t-test for the bivariate analysis. And this determines the statistical difference across the groups. And so we'll review this command briefly and run it for just one of our variables. And we're going to use age again just for consistency's sake so we can compare the results as well. So first you tell Stata that you want a t-test, and then you want to indicate your continuous variable, which is age, and then you indicate the group variable, which is the categorical variable with 2 levels. And so in this case, it's our outcome variable satisfied by. So with our output, we'll notice that our p-value is exactly the same as what we got in the one-way ANOVA. So it's 0.0087. And so our result, again, is statistically significant. You'll also notice that the t-test provides us with a little bit more information. So with the t-test, we get a 95% confidence interval for both low and high satisfaction, which we didn't get with a one-way ANOVA. And so for more information on the two-way tabulation, you want to search help to tabulate two-way. For the t-test, you can search help t-test, and the one-way ANOVA commands, you can search help one-way, and it will give you more information on these statistical methods. And so going back to our do file, we're finally ready to perform our logistic regression. So scrolling down to this. First, we want to run the logic regression and produce estimates in terms of logit's coefficients. As we had said in the PowerPoint, the first thing you want to do is to specify your logit command. Next, you want to specify your outcome variable, which is your binary or dichotomous variable. And so for our case, it's level of satisfaction. Then you want to specify your independent variables of interest. And as a reminder, for our categorical variables with more than 2 levels, we need to indicate that they are factor variables by adding the prefix I dot before each of these variables. So we are doing this for HIV, syphilis, as well as ethnicity, because they all have more than 2 levels. And we can take some time to confirm this. So we tab 1 because we want the tabulation of multiple things. We have HIV, syphilis, and ethnicity. Okay, so looking at our tabulations, we can tell that and confirms what we said previously, that these variables have more than 2 levels. So we need to indicate that they are factor variables in our regression. So let's go ahead and run this command. Okay. This is our output. Stata also produces other information in addition to the regression coefficient. It gives us information on the number of observations included in the analysis. In our case, all observations were included. If we had missing data, it would only run the analysis on cases with complete information, so cases with no missing data on any of the variables. It also tells us our model fits. So the model chi-square test represents a significant improvement in fit relative to the null model, which is also the intercept-only model. And so the p-value of this is 0.000. So it tells us that our model is a significant improvement over the null model. And then the next thing we have information on is the McFadden's pseudo R-square. And this gives us information about fit as well. It can be interpreted as a percentage or proportion of improvement over the null model. model. And so in our case, our pseudo R-square is 12.65%. So this tells us that our model is about a 13% improvement over the null model. The output also gives us information about the unstandardized coefficient in our first column, standard error in the second column, the Wald statistic in the third column, our p-value in the fourth, and in the last two columns, it gives us information about the confidence interval for each of our predictors. And so the significance, which is our p-value and our confidence intervals, is based on the Wald statistic and is calculated using this Z, the Wald statistic. So the unstandardized coefficient gives us information about the slope for each predictor, as well as the intercept, which is our underscore cons. And so we had said previously that a positive slope indicates the log odds of being a success or falling into the target group. And this increases with increasing values in the covariate variable. A negative slope indicates a negative association or log odds of being a success or falling into a target group. And this decreases with increasing values in the covariate variable. And if a coefficient is equal to 0, that means that you have no association. And so based on this, we're going to spend some time interpreting the outputs. We can actually start from the top instead. I was going to suggest we start with our statistically significant findings. But starting from the top, gestational age has a p-value less than 0.05. The p-value is 0.010. And so we know from this that our findings for gestational age is significant. You also notice that the coefficient is greater than 0, so we have a positive association. And so just age is a positive significant predictor of the log odds of having high satisfaction. Gravida's p-value is 0.022. So this again is significant. However, gravida's coefficient is less than 0, and so we know that it's negatively associated with our outcome. And so we can say that gravida is a negative and significant predictor of having log odds of high satisfaction, or a significant predictor of the log odds of having high satisfaction. Going on to parity, parity's p-value is greater than 0.05. So this is not significant, but the association is negative. So parity has a negative association. So it's a negative predictor of the log odds of having high satisfaction, but it's not significant. Number of A and C, p-value is less than 0.05. The coefficient is greater than 0. So we have a positive association. So it's a positive significant predictor of the log odds of having high satisfaction. So HIV is also not significant. Syphilis, the levels of syphilis are not significant. Same with the type of delivery, same with age. Education, on the other hand, has significant predictor because the p-value is less than 0.05. And so we can say that having secondary or higher education is a positive and significant predictor of the log odds of having high satisfaction. And so looking at the remaining predictor, so marital status is not significant, work is not significant, and ethnicity also not significant. And so from our output, we can see that gestational age, gravida, number of ANC visits, and education are significant, but all other predictors are not. So as we said previously, and also you may have noticed from the interpretation of the coefficients, we're only interpreting the direction of change or association. The regression slopes for the covariates can determine the direction of change, but should not be directly interpreted as the amount of change that we see. And so to interpret the amount of change, you want to run the logistic regression and report the odds ratio. Going back to a do file so we can run the odds ratio. In the PowerPoint, we talked about two different ways to do this. So the first is what we present or highlighted. You want to first use your logit command, similar to what we use when we're running the odds. Next, you list your outcome. Then you list your independent variables, and at the end you add comma OR. And so this tells data that you want the odds ratio. Alternatively, you can use just the logistic command, list your outcome and then your independent variables of interest and run that. And so these two commands produce the odds ratio, which is the effect coefficient of the anti-log of the odds or regression coefficients that we found previously. And so let's run this. This is our output. And we're going to just focus on our significant predictors in this for our interpretation, since we have an idea of how to interpret our odds ratio. And we'll also look at it again in the PowerPoint. And we'll move over to the PowerPoint after we interpret these findings. And so for gestational age, the odds ratio is 1.18. Thus, we have a positive association because our OR is greater than 1. And so this tells us that the odds of a woman being highly satisfied increase by a factor of 1.18 with every unit increase in the gestational age of pregnancy. Or alternatively, we can say that our odds is increasing with each increase in our predictor. The next significant predictor is gravida. And so the odds ratio for gravida is less than 1. It's 0.87. And so this indicates a negative association. And our OR tells us that the odds of a woman being highly satisfied changes by a factor of 0.87 with every unit increase in the gravida of a woman. The odds is decreasing with each increase in our predictor. The next is number of ANC visits. So our odds ratio is 1.37, and this represents a positive association. And it tells us that the odds of a woman being highly satisfied increase by a factor of 1.37 with every unit increase in the number of ANC visits. So our odds increases with each increase in our predictor. And the last is education. So our odds ratio is 2.66. And this tells us that the odds of a woman or a more educated woman, that's a woman with secondary or higher education, the odds of her being highly satisfied is 2.7 times the odds of a woman who is less educated. So someone with no primary education. And so our odds is increasing with higher education compared to lower education. And so now that we've interpreted these findings, let's move over to the PowerPoint to also explore different ways in which we can interpret our regression results. So in the demonstration, we reviewed univariate analysis, bivariate analysis, as well as logistic regression. Now we want to spend a little bit of time looking at the odds ratio and another way in which we can interpret it. Before we move on, let's briefly look at the output we received when we conducted the analysis in Stata. So highlighted, we have the model chi-square test, and we found out that our model is a significant improvement relative to the null model, which is the intercept-only model. The McFadden pseudo R-square told us that our model was about a 13% improvement over the null model. So now let's focus on the odds ratio column and the 95% confidence interval column in the orange boxes. We know a predictor is significant because our p-value will be less than 0.05 and the confidence interval will not include the value of 1. And so our first significant predictor is gestational age. The p-value is 0.01, which is less than 0.05, and our confidence interval does not contain a value of 1. Gravida in the same way, p-value is less than 0.05, and the confidence interval does not include the value of 1. Number of ANC, our third significant predictor, has the same thing. And the last significant predictor, education, also has a p-value less than 0.05 and a confidence interval that does not include 1. And so we're going to focus on these 4 significant predictors going forward. First, looking at gestational age. Our odds ratio for gestational age is 1.18. And so this is a positive association because our odds ratio is greater than 1. And this tells us that the odds of a woman being highly satisfied increase by a factor of 1.18 with every unit increase in the gestational age of the pregnancy. Also, it tells us that the odds is increasing with each unit increase in the predictor. So we can also interpret or present our results at our odds ratio as a percentage. And so to do this, you want to subtract 1 from the odds ratio. In this particular example, our odds ratio is 1.18. So 1.18 minus 1 multiplied by 100% gives us 18. So we can say that for every increase in gestational age, the predicted odds increases by 18%, or the predicted odds are increasing by 18% per unit increase on gestational age or in gestational age. And we can do this same thing for the remainder of our significant predictors. For gravida, we can interpret the odds ratio we get in our regression either as the output that we get or as a percentage. So the OR for gravida is less than 1. So we know it's a negative association. And it tells us that the odds of a woman being highly satisfied changes by a factor of 0.87 with every unit increase in the gravida of the woman. So our odds are decreasing with each increase in our predictor. And as a percentage, we'll say that for every increase in gravida, the predicted odds of high satisfaction decreases by 13%. Similarly, for the number of ANC visits, you can use the same method of interpretation. So the OR is 1.37. Thus, we have a positive association. We know that the odds of a woman being highly satisfied increase by a factor of 1.37 with every unit increase in the number of ANC visits she had. Our odds is increasing with each increase in the predictor. And if we interpret it as a percentage, we'll say that for every increase in the number of ANC visits, the predicted odds increases by 37%. For educational level, the interpretation is slightly different because we're comparing one level to the reference group, but the way we describe the association remains the same. So the OR is 2.66, which is greater than 1. So we have a positive association. We know that the odds of a more educated woman, someone with secondary or higher education, the odds of her being highly satisfied are 2.7 times the odds of women with less education. So our odds is increasing for more educated women compared to less educated women. Alternatively, you can say that women who have secondary or higher education are more likely to be highly satisfied compared to women with lower education. As a percentage, we can say that for more educated women compared to less educated women, the predicted odds increases by 166%, which we calculated by subtracting 1 from our odds ratio and multiplying that by 100%. After running our model, we can also run the Hosmer-Lemon-Short test, which tests our estimated model to one that has a perfect fit or a saturated model. So if the test is significant, then we have evidence that our model was misspecified. But if the test is not significant, then we have evidence that our model is adequately specified. So to run the Hosmer-Lemon-Short test, we tell Stata to estimate the goodness of fit for 10 groups, and this is the output that is produced. Our p-value in our output is 0.6509, which is greater than 0.05, so it's not statistically significant. And so this tells us that our model that we used is adequately fit or adequately specified. We check for collinearity in our model using a package developed by Philip Ender. The package computes several collinearity diagnostic measures, including the variance inflation factor, or VIF for short, tolerance, eigenvalues, condition index, and R-square. And we are interested in the tolerance, VIF, and R-square. And so to use the command, we first tell Stata to use the column package, then we list the independent variables in the analysis. And so in doing so, we don't want to include the factor variable because the package does not allow for factor variable or time series operators. So we didn't add the prefix I dot to our factor variables. And so what we see is our outputs. So we're interested in the tolerance, VIF, and the R-square values. So the tolerance values in the third column are computed as 1 minus R-square, where each predictor K is regressed onto the remaining predictor. So taking gestational age, for example, gestational age will be regressed onto the remaining predictors, so gravida, parity, number of ANC, HIV, syphilis, and so on and so forth. So tolerance values closer to 0 signal greater problems, and values of 0.1 or 0.2 are often regarded as signifying serious problems. if we're using just age again as our example, if we regress just age to the other variables or on the other variables, the R-squared value is 0.0214. And just age is not a linear function of the other predictors. Our tolerance value is 1 minus 0.0214, and that gives us 0.9786. The variance inflation factor for each predictor is the inverse of the tolerance value. So our VIF is 1 divided by tolerance. And so for the VIF of just age, we compute it as 1 divided by 0.9786, and that gives us 1.02. So different researchers have different benchmarks for determining multicollinearity. Some researchers suggest that VIF scores of 10 indicate the presence of collinearity between covariates, where others have suggested a cutoff as low as 5. So we're going to go with a more conservative estimate of 5. And so based on that, we can say that our analysis doesn't have any issues with collinearity because the overall score, our mean VIF is 1.10. And for the individual VIFs we have in here, they're all under 5. And in general, we see no issues with multicollinearity among our predictors based on our VIF and tolerance values. For categorical variables with more than 2 levels, we can go a step further and test for the overall effect by using the post-estimation command in Stata, test parm or test. And so with test parm, and we'll use the syphilis as an example. So for test parm, you can use the entire variable, so indicating that it's a factor variable. So test parm, prefix I dot syphilis. Whereas with our test command, you need to list the coefficients in the variable. So we need to list the different levels. So the second level in our syphilis variable, and the third level. You don't include the reference group. We had 3 different variables in more than 2 levels. So we just talked about the syphilis. The next, we can do it for HIV and then do the exact same thing for ethnicity. We know the overall effect for all these 3 categorical variables are not significant because the p-values are greater than 0.05. And so it goes in line to what we saw in our output where each individual level wasn't significant. And so we now know that in addition to the individual levels, the overall effect of each of these categorical variables are not significant. So now that we know the findings of our logistic regression, as well as the univariates and bivariate analysis, we may want to present this information at a conference or in a publication or at a seminar. So you don't want to present the Stata output that we got in Stata. So rather you want to format it into a table. And so there's a program called TabOut, and this program can be used to make tables for univariate and bivariate analysis, and it makes the tables ready for publication or almost ready for publication. TabOut creates tables with counts and percentages, as well as summary tables with means, medians, standard errors, etc. It exports the tables into a Word document or Excel file or text file, and I believe an HTML. And as a user, you have the option to choose how you want to export the file. It's a free program, and as of today, there are 2 versions. So version 2 of TabOut can be downloaded using the SSC install command, and version 3 can be downloaded on the TabOut website. So on the TabOut website, you have to download the ADU file. And for more detailed information on the command, visit the website listed at the bottom of the page. And the commands that we used for these analysis, so the TabOut commands we use for these analysis are presented in the do file. Although TabOut is great, as we said, we still have to edit our tables for it to be publication ready. So in our bivariate analysis, we wanted to present the percentages as well as the means in one table. However, in the current versions of TabOut, percentages and means cannot be requested in the same table. So we had to combine two tables into one. So these two tables we see are what we produced using tabout. The table above displays the percent distribution of our exploratory variables, and the table below, the second table, presents the means. So these two tables were combined into one table. And in our final table, we're presenting the percent distribution frequencies as well as the means and standard deviation. The standard deviations were calculated directly in Stata and do not use a tabout command to produce it. So similarly for the bivariate analysis, we produced two tables, one for percentages, one for means. The one above presents the bivariate analysis between the outcome variable, level of education, and the categorical independent variables. The table below presents the analysis between the outcome variable and the continuous variables. So after combining the tables, this is our final table. And in general, tabout makes tabulation process a lot easier and less tedious. That way you avoid entering each number into Excel. So it's a great tool and I recommend that you use it. So for the regression tabulation, we could not use tabout, so we created our tables manually using Excel by typing out all the values from the regression output. And this is our final table that was produced. To answer our research question, controlling for all other variables, we found that gestational age, number of AMT visits, and having a secondary or higher education were possibly associated with high satisfaction. Gravida was significantly and negatively associated with having high satisfaction. Thus, we need to consider the policy or program implications of these significant predictors when attempting to increase a woman's satisfaction with maternity care services in general. We need to consider these. They are important. To summarize, logistic regression is an analytical approach used to model a dichotomous outcome variable, and it has extensive use in the healthcare and social sciences. It predicts the probability of success of an event or falling into a target group. It's easy to use and produces robust estimates. We can get either the odds or the odds ratio. So our odds is the change in the expected log odds relative to the unit change in the predictor, holding all predictors constant. And so for the odds, you want to interpret it for the direction of change and not the amount of change. The odds ratio is the change in the odds of success relative to the unit change in the predictor, holding all other predictors constant. And this you can interpret for the amount of change as well as the direction of change. Your odds ratio values are going to fall between 0 and positive infinity. And also, when you're presenting the results for the odds ratio, you also want to present the 95% confidence interval. So this is the end of the logistic regression video tutorial. As we mentioned at the start of the presentation, we have several resources available: a background information sheet on logistic regression, the presentation used today, as well as a data do file and sample data sets used in the presentation. Thank you for your time and attention. We hope you learned useful tips about logistic regression and encourage you to use it as a tool when you analyze routine data for evaluation and research.